So today I wanted to show that a finite integral domain is always a field. So first I want to start with the definition of an integral domain because some authors use different definitions. But the one we're going to use today is an integral domain is a commutative ring without zero divisors. And then some authors have this and some authors don't have this with 1. So the identity element under multiplication. Today here we're gonna discuss the version where we don't have 1, because this theorem is actually true even if you don't have 1. Then what that means is that if you're taking a class and if your professor includes this 1 as part of the definition, then you can still use this argument and then you'll be fine. So I'll prove this one. Also, one thing is that integral domain is not a zero ring. Not a zero ring. Or this. Because, yeah, it just doesn't really make much sense to discuss this as an integral domain. So yeah, let's get started. So let's say I'm just gonna call this R. Let's just move this a little bit so I have enough space. A commutative ring R without zero divisors. What's missing here? Like, what properties do we need to add to R to show that R is a field? So what's missing is first the existence of 1, which some professors might include, but here we're assuming that this definition doesn't include 1. And the second, every non-zero element for all x in R. If x is non-zero, there exists the inverse of R. The inverse of x under multiplication is in R. So we want to show these two. And again, if your professor includes this in the definition, you can skip this part, the first part of the video. And then how are we going to get this? So obviously that's not true for any integral domain, because if every integral domain has those properties, then, you know, an integral domain is the same as a field, so we wouldn't be discussing it. What's special here is that we are assuming that R is finite. So this property that R is finite, this is gonna give us these two nice properties. So first, let's show that 1 is in R. And we are going to start by making use of this property that R is finite. So let A1, AN denote non-zero elements in R. And what I'm gonna do here is to think of a sequence A1, 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 A2, A1, A3, A1, A4, up to A1, AN. So basically, just take every element in this sequence or set and then multiply A1 from the left side. Well, actually the side doesn't really matter because we're saying that R is commutative, but you know, just for the style, we'll have this. And I'm going to claim that every element in this, they're distinct. The proof is actually pretty simple. Suppose that A1 AI equals a1 aj for some I and j. Then this implies that a1 a, just gonna skip some step, but aj equals 0, since we know that our integral domain doesn't have any zero divisors, and then we are assuming that a1 through an are non-zero elements, a1 can't be 0, then this is 0. So we have ai equals aj. So these two multiplications, they're the same only if ai and aj are the same thing, which means every element, any pair of elements in this set are different. So we started with n elements here, and then we have n elements here, and then since every element in these sets, they are all non-zero elements, and R has no zero divisors, that means each of them has the exact same set of elements. Then what happens is that there's an element somewhere here, a1 aj, or I'm just gonna call it ai, I guess, because we don't, a1 a, and then this element has to equal to a1. We don't know what I is, but since we have two sets containing the exact same elements, then they have to correspond, right? So this a1 is equal to a1 ai for some I. So I'm gonna write it down, and I claim that this ai is actually 1. The proof is actually pretty simple. For all aj, we want to show, what we want to show is this, ajai equals aj. And this can be done very simply by considering aj a1 equals aj a1 ai. So this is obviously true, because a1 and the a1 ai, we said that these are equal earlier here. So now we have this, and we can use the distributive property minus a I, sorry, okay, I'm not gonna skip one step. So we are gonna have 0 equals aj a I a1 minus aj a1. This is equal to a j, j and I, a j a I minus a j a1. And then again, this ring has no zero divisor. A1 is non-zero element. Then this must be 0. That means aj equals aji. aj equals ajai. Then ai is indeed the unity, the identity element. So yay, we found it. So we just proved that 1 is in R. So now we can move on to the second part, which is that every non-zero element in R has an inverse under multiplication. And then we are going to use the fact that this group is finite again. I'm going to mark this part. So the next part is inverse. And actually the argument is very, very similar to the first one. So let a1, a2, a3, an denote non-zero elements. This is starting to look familiar, right? Non-zero elements in R. And then, we want to show that each one of these elements has an inverse. So let's just say we're going to talk about AI. Let AI be given, obviously from this set. And what I'm going to do is to multiply AI multiply it to each element. A3, AI, AN. Again, exact same argument as the one above. These elements are all distinct. And then, because R has no zero divisors, and then none of these elements is zero, so when you multiply, you still get non-zero elements. So again, we got two sets containing the exact same set elements. And then previously, we showed that one of them is 1. So we have a, what I'm going to call it, AJ, which is 1. We don't know what J is. Actually, it doesn't really matter. All we know is that there is an element called AJ, which acts as the identity element under multiplication. And since these two sets are the same, there is an element here. I'm going to call it AI, AK, such that this is equal to 1. So we just found there exists K such that AI, AK equals 1. And then since R is commutative, this also implies that AK, AI equals 1. So AK is the multiplicative inverse. So from these two arguments, we just showed that if you have a finite commutative ring R without zero divisors, finite commutative ring, then from this property that R is finite, we can show the existence of the multiplicative identity and the inverse for each non-zero element. So R must be a field. R is a field.